Hi and welcome. This time around, we have sort of multiple things on the agenda. I thought I'd start by thanking R. Stephen Lang for the sticker from Shark River Machine. He's got a YouTube channel that I really enjoy, so go check out his channel, and I add the sticker to my wall. I also got a great deal on this Michu Toyo comparator stand, and it's really smooth, polished and lapped measuring surface on it. Very cool. Use that if I have to make multiple parts and they all have to be within a certain tolerance. That's kind of a neat purchase. I thought the design was really interesting because they use two pieces of spring steel that are large and flat, which only allows motion in this axis. Obviously you can't go this way because it's very sturdy in that direction, and you can't go this way, also very sturdy in that direction. Just up and down, just the Z-axis. Very nice design, and reminiscent of some things I've seen on some other channels. Very nice design, very sturdy, doesn't bounce around anywhere near as much. The normal style that you see all over the place is this granite base stand, and this one you lock the top piece and you leave the bottom one floating, and then you use this as a fine adjust. The lock piece is the top piece is the coarse adjust, but I find there's so much flexion in this sort of design that I end up snugging both, and I just tighten this against the tightened bar to just deflect it ever so slightly to get my zero set, especially when you're doing half thousandths or tenths. So anyways, this is a much better design, and I like it a lot better, so I will be giving this to a friend. Coming back to my number 1D6 Sjogren hard-hinge chuck, this is a heartbreaker. So the more I played with it, I couldn't get a 5C collet to seat. I called Hardhinge about it, and sure enough, it is missing the thrust bearing out of it. So I ordered the thrust bearing, which Hardhinge wouldn't tell me what the size bearing was. They charged me a generous $200 for the thrust bearing, which really annoyed me. Still wouldn't work. Found out that even though every time I called Hardhinge, which was on 3 separate occasions, I told them I have the number 1D6 model speed chuck, and is the 5C thrust bearing the right thrust bearing? Well, it turns out that the 5C thrust bearing is not the right thrust bearing, because the 1 in front of the D6 designates this as a 1J chuck. And the 1J chuck, I don't have any, but they're very much like 5C chucks, except they're Hardhinge exclusive, I believe. And they are not cross-compatible. I think the 5Cs are a little bit longer because I could never tighten the chucks all the way in this collet holder. So very disappointed, because Hardhinge could have corrected me, and they sent me to a third party to get the bearings, and they never corrected me. I always talked to their supposed Sjogren Hardhinge speed chuck expert, and none of them ever said anything. Also, I've been told by some of the comments online that these little Zerk fittings, not Zerk fittings, but the ball bearing, normally an oil fitting, can be used with grease. And just based on the way this was working internally, I think grease is a much better solution, because among other things, when I put oil in here, the first time I ran it, it spun oil out all over the place, even though it was Vactra 68, and got it all over the handle, which was no fun and messy. So I'm a little disappointed in Hardhinge for not telling me, by the way, that is not a 5C collet. I could have sent it back a long time ago. Unfortunately, I don't want to buy a bunch of 1J collets, so this is going back to the eBay seller that sold it to me. Next up is this new find, is this Sato Hardness Tester. I've been looking for one for a while. Let me pull back here. So I got this Sato Hardness Tester. It was brand new in a crate, although it had been sitting in the crate for like 10 years. Something like that. Anyways, they don't make them anymore. Sato Seiki, it's a Japanese company, and it's a Rockwell B&C hardness tester. Works great, very repeatable. On one side over here, let's see. On one side they have a air pot, and an air pot is just a piston with the air shut off through a needle valve or some valve of some kind, so you can control how quickly it sits down. You can see, and you can control how slowly it goes down. And that's to meet the Rockwell standard for the amount of force. All right, so the way you use this is you pop your test block in to figure out whether the calibration is right, and you try and get your indenter over a place where there isn't a previous indent, and then you tighten the workpiece into the diamond indenter. By the way, the diamond indenter, you use a diamond cone for Rockwell C's, use a 1/16 ball for B, and it's got all the other different indenters here, but this scale only does B and C. So you preload it by tightening this until the little hand here, as it rotates around, ends up on that dot, and that tells you your preload force is correct. Then you zero your dial, like so, and then you release the force, and you wait for a prescribed amount of time, which I'm not exactly sure what that is, mostly until the hand stops moving. There, you can actually look in the Rockwell spec and see what the time is. And once it stops moving, then you release the force, and where the indenter goes back to tells you what the hardness is, and this says it's 35 3/4, and this test block says it should be 36.3 plus or minus 1. And since the materials aren't homogeneous, what they do recommend is that you do the test 3 times and take the average, and that will be your hardness. That's even in the spec. So I'm very excited to have this, because now when I do heat treating, I can tell whether it's working or not, or if I do case hardening, all the above. If I'm wondering whether a nut or a bolt, how hard it is, I want to test that. I can test that as well. I played around with this a whole bunch, and it repeats really well when you get the right disc and make sure you don't hit an indentation and wait till it stops moving, etc. So I'm pretty pleased with it. Finally, this week I've got a bunch of parts I need to make for a customer. This one's out of aluminum. This is Delrin. This is Delrin. This one's also Delrin, and a bunch more out of aluminum. There's a pretty simple one, kind of a big part out of 1/4-inch plate. This one's also 1/4-inch plate with some relief cutouts and drilled and tapped holes. And what I find particularly interesting about this is what I did is I've shopped my services out, and people are getting back to me and then wondering how much things are going to cost. And I think to myself, well, I sort of know what I'd like to make an hour, but how the heck do I figure out how long these are going to take? So I sort of guessed here. I guessed that dimensioning this stock would take about 15 minutes. Drilling and tapping both ends, 20 minutes. Relieving these sections, 15 minutes. That might be a bit short in time. This is 1/2-inch stock, and this section are 1/4-inch thick. You can see in this profile over here. There's drill and ream the center hole here. That's 5 minutes. And that came with 55 minutes apart, and I need to make 3. Now what I thought was, hey, you know, if I take one piece of material and I get some of the engineering plate that's pre-surfaced on 2 sides so that they're flat and parallel to 1/2-inch thickness across the whole thing, then I could relieve the material for all the parts simultaneously, which is what I'm going to intend on doing here, and cut the parts out, then dimension the thickness, drill and ream, drill and tap, and I should be done. And that can speed this up a whole lot. And what I'm dealing with the customer was, I said, look, I think these are going to take me 55 minutes apart. But if it takes me less time, I will give you back the difference, because this is what I'm expecting an hour. I'm charging very little, so an hour relative to prototype machinists. My understanding is in the area, prototype machinists charge somewhere between 150 and 500 an hour, depending on, you know, how complicated the parts are, the toughness of the material, and how precise everything has to be located. I'm charging 60 bucks an hour. Now, I'm a hobbyist, so I don't have a problem with that. This part, precision, is very important. So you'll notice that all of his values are listed at 3 digits here. So I asked him, do I have to have everything plus or minus 1,000th? And he said, no, only things that are spec'd, like the hole, that has to be within 1,000th. As far as diameter, but the rest can be plus or minus 5,000th, and you need to take that into consideration in the amount of time something's going to take you, because the setup is a lot more finicky if you have to have super precision on every part, on every feature. So that factored into it. I'm trying to figure out ways to make things more efficient, because that's always fun. So that's where I'm at. I don't know if anyone else has had this problem, if you've tried to shop your services out, but figuring out how much to charge is really tough. And if I had to make a living at it, the last time I guessed one of these projects, I was off by a factor of 2 the amount of time the project took. That was that plastic dog treat thing that didn't work out so well. I ended up eating that whole cost because that was on me. I should have known better than use that material and let it warp. I didn't know to say no, and neither did the client. So I just ate my time and chalked it up to a learning experience, which I did. I learned a lot, so I have no regrets. This also, I've given the client, telling them that I expect this part to take 55 minutes, so 3 parts should take 2 hours, 45 minutes. If it takes me less time, I won't charge you as much because I'm looking for the hourly rate, and just that's, I like making parts, and I want to figure out this how to estimate parts. So I'm sure some of the old timers are laughing because it probably took them a bit of time too. I don't think anyone naturally has a knowledge of how long something's going to take. So I'm actually going to use a timer for each part and see how close I can get to accurate. Alrighty, so I've got my rough stock here, and I need to dimension it to 5 inches by a little over 6 inches so I can cut 3 2-inch pieces out of it. So I need to get these 2 sides flat and at least one of these other sides flat. In order to hold it vertically in the vise to give it some support, I've grabbed some of this ATP aluminum, which is ground aluminum plate, engineered plate, and it's Blanchard ground on both sides so that they're flat and parallel and very, very close to precise. So what that lets you do is hold things in the vise without worrying about them bending, you know, leaning to one side or the other like a normal extrusion would be. This stuff is very, very good. So I recommend if your local supplier has some, buy some scrap pieces like I did, cut them out. You can use them for all kind of fixturing. I'm using this way. I use them lying flat along the mill bed here to put parts on to hold them flat, clamp down on, and I know that they're going to be flat and square, which is great. I don't care about these sides here. All I care about is these 2 surfaces, the large flat ones. So anyways, handy to have around the shop, highly recommended. Alrighty, so I got a face mill loaded in here, and I noticed that I sort of made my overlap symmetrical on both sides, but what I'd like it to be is a little bit, actually that's what I need, because I need to measure this thickness when I'm done, because I'm looking for a precise 5 inches within plus or minus 5 thousandths, but obviously I'm going to shoot for a little better. Right now, I can't remember where this is. I believe this is just a bit over 5.3. So we've got some material that can come off. I'm using a face mill here with wiper inserts, so I'll be curious to see what kind of finish I'm going to get here. What I neglected to say is that the bottom side of this part was cut in what's like a sort of moving table saw at my metal distributor, and so it's a pretty flat surface. So I've got that against the bottom of the vise. I'm going to make the top side flat, take off maybe 30-40 thousandths, and then I will flip it over now that I know that this is flat for sure and perpendicular to these faces, and then I'll set that face on the bottom and then get my final dimensioning based on removing material from the other side. That should be pretty close. Also, in figuring my time, I didn't start the timer while I was doing the setup, which is really a little bit unfair, but I was also setting up the camera. And I don't know if any of you that have shot YouTube videos, you know you can spend at least double the time setting up shots and making sure that everything's right for the camera and actually not doing work at the same time, and that's what's happening here. I'm wondering if this is going to be stiff enough, so I'm kind of curious about that. Try 25 thousandths. It may be a bit much. What I may need is to cut some supports that are taller. And the vibration's not too excessive. Surface finish is pretty good. So what I'm going to do is I'm going to pop this guy out of here. I'm going to take it over to my Scotch-Brite wheel. I'm going to deburr this side, or I could do it here, and flip this 180. So upside we have the sawn surface, and measuring these, they're about 2 thousandths difference from one side to the other. not bad at all considering over 6" and it was sort of a table saw design. It's not an insignificant risk that when you pull this part out to deburr it that you are going to get chips in the bottom, so be careful that you don't get any chips underneath it, because obviously that will tilt the part and ruin it. So I'm going to do a few more passes here and I'll bring you back. Here's another observation you might find interesting. So I might have better luck if I didn't use a face mill to do this. I thought I'd try it with a face mill just to see how it worked out, and I'm actually getting a decent finish, turning over a nice burr on the edge there, but that would probably be no matter what cutter you use. But the larger diameter cutter you use, the more the cutter is going to be approaching at nearly a perpendicular angle to the material as it cuts. If I used a 1/4" diameter cutter, as it hit the cutting surface, a lot of that force would be directed straight down the length of it rather than perpendicular. With such a large diameter part, when this cutter comes in, you can see that it's nearly perpendicular to the part, which causes a lot of wiggling back and forth. Even as supported as I have it here, I probably would do better if I went all the way up to just barely under the top surface there. So that's a consideration. So I'm going to switch to an end mill. Alrighty, so now I have a 5/8 end mill here, and it's a high-speed steel one, and we're going to do a much deeper depth of cut. We're going to shoot for 40 thousandths here, and compare the difference in sound between this and the face mill. You'll notice it's a lot less noisy because the cutter is coming, the tooth that's cutting is coming mostly in, not so much at a perpendicular angle. So I'm actually getting a much quieter cut than a larger diameter cutter. Another tip, if this depth or this material removal was, the consistency of depth was extremely important, you were looking for very high accuracy, I wouldn't put my Weldon shank end mill in an R8 collet, because under extreme forces they can tend to pull back into the collet. Instead, I'd use a fixed depth holder like this that goes on the Weldon flat and locks down. With that kind of holder, there's a lot less likelihood of the end mill shifting in the collet, which I've had happen before. Can totally hose you. Fortunately, this is aluminum, and so it's probably not so much of a problem, but it definitely can be. Alrighty, so hopefully you can see that. There's the thickness. Looks like maybe 1/2 thousandth. Should be using calipers if I really want, micrometers if I want extreme accuracy. Not what we're going for here at all. Just wanted to show you this is one technique you can use. I've got another one I use in an upcoming video that you should see. So now I've got these two sides are flat and parallel. These two sides are flat and parallel. As long as I'm here, I'm going to give myself a head start, and I'm going to go ahead and square up this side and square up this side, not to any particular dimension this way, just enough so that I'll have two parts that have sides that are already flat as I start to work on them, because that costs me almost nothing to do it at this point. Even though I only have a little bite on it here, I'm only holding an 1/8 inch of material. I'm going to try and use this face mill and see how it works out. If it doesn't, we'll switch to an end mill or whatever's necessary. So to set my Z depth, I found my 0 here using some shim stock, so that's 21 thousandths. And come back up 21, and that should be 0. And then we're going to find our 0 in this direction. So next we're going to try and hog out a fair amount of material. We'll only go down a little bit. We'll do in multiple passes. So right now, let's go down 50 thousandths. We have to go a total of 250 thousandths. Let's try 50 thousandths. And I need to go in on one side. We'll try this on the small side first. 1.75 inches. And we will go in 1.73 and leave 1.74. We'll leave 10 thousandths for a finish pass. And I'll lock off this. Leave my Z-axis alone for the moment. So we're just going to try and take off 50 thousandths depth of cut, 1.75 total width, and 1.74. We'll do the last 10 thousandths on the final pass. We're going to work our way down to take a total of a 1/4 inch of material off here and see how that works out. We'll go slowly. No vibration to speak of. My concern is when the material gets a lot thinner that this becomes much more problematic. Evaluating the depth of my cut to make sure it's 1.74. I'm using a depth micrometer here and it's right on the money, 1.74. So that's good. I'm also curious about consistency of thickness, because if your mill head trim is at all like this, you may cut a little more on one side than the other. I'll check that just to make sure we're okay. All right, first side done. I'll take this over and deburr it. I'm going to flip it this way and I'm going to do the other side, and we should be good. And we'll have all 3 parts done at the same time. Final finishing pass. Taking off 2 thousandths. Alrighty, so here's all 3 parts. I'll dimension the last one. I have to take more off the last one. Got a flat side on that side, a flat side on this side. So dimension one side on this one side on this one, 2 sides on that one. Of course, I dropped it. That's just amazing. So I'm gonna take this over the bandsaw and cut these parts off, and I'll be right back. All right, so now I got 2 parts loaded simultaneously, and I need to dimension the width on each one of these. These are the 2 parts on the end, so this is an inside, this is an inside. So these are already finished, so I'm using these as reference surfaces, and I'm going to bring these other sides in. So we're going to start on this side, and the reason I got 2 parts in is that stops the vise from canting this way, so your load's equal, because I need the part to hang over the edge. And right on the money. Absolutely perfect. Okay, one more to go. This one has to have both sides done. So this last one, I'm just going to do a quick pass on one side to clean it up, flip it 180, and then I'll bring the other side into final dimension. I guess I should know how much I've got to lose here. I usually just take off the minimum it takes to clean up. I've got about 150 thousandths. I purposely left this one a little large. So, all right, so these are reject parts. The first 3 I made, I relieved this section, and when I measured thickness from outside to inside, the inner portions on both sides were much thinner than the outer portions by like 4 or 5 thousandths, which really irked me. And I thought, geez, what happened? Did it lift up in the over the parallel, or what happened? Turns out I ignored a very important feature when you're milling, which I should have put this flat on the mill table, but since I held in the vise, when you squeeze the vise, this is going to want to buckle a little bit. Now when it's 1/2 inch, it wasn't a big deal, but once I started reducing this down to 1/4 inch, it started to buckle more and more, and when it buckles up in the middle, it means it cuts off more material in the middle than it does on the outside edges, and as a result, it's not equal. So when I did the second set of these, I took clamps off the mill table with parallels underneath and clamped the center section down so that it didn't buckle up, and I got within 1/1000th. Lesson learned. Probably should have milled this flat on the milling table. I was just kind of lazy. I wanted to do it in the vise because it seemed like it'd be faster and more efficient. But in the long run, I saved myself time and in one part and then had to redo it, so I lost a lot of time. Alrighty, so here's the final parts, and I didn't show you the drilling and reaming of the center hole or the tapping of all 4 sides of these guys. Because it didn't seem like that would be reasonable. You've probably seen that a million times before, so there's not a lot of interest there. I tried just to keep this project down to showing things that were different or interesting. What I did find is that my time estimate was really poor. Dimensioning stock was pretty close to 15 minutes. Tapping was closer to an hour and change. Drilling and reaming was, I don't know, 15 minutes, 10, 15 minutes. That was pretty close. Relieving was a lot longer. It was a couple hours. So I didn't really estimate very well, but lesson learned, and hopefully it'll be better next time. Anyways, I learned a lot in this project. Scrapped some parts, had to do it again, but overall I learned a bunch, and I'm glad I did it. I've got a bunch more parts to make, as you can see underneath the sheet. So if there's some interesting parts of these, I'll bring you back. Thanks for watching. Hope to see you next time.